Hi, in today's video we're going to be talking about the momentum progress check. This is an assignment from last week. I posted and hope that everyone would attempt to do so we could get a sense of how much you knew about momentum. So we're just going to cruise through these real quick. Check to see your answers versus my answers. And hopefully this will make some sense to you when you go back and look at it on your own. So let's talk about number one. Number one says, when can a golf ball have the same momentum as our bowling ball? Well, if you think about a golf ball is relatively small and dimpled. And then you think about a bowling ball, much bigger. Okay? When can these two have the same momentum? Well, the thing about this is that a golf ball is a very small object. It has a small mass, where a bowling ball has a really large mass. Is it possible for them to have the same momentum? It's a great question. Well, if you think about momentum, mathematically, P is equal to M times V. So if these two have to have the same momentum, if this one has a small mass, this one has a large mass, well, what do you think has to be true about their speeds? Well, if their momentum are going to be the same, if you have a bowling ball that has a very large mass, it has to be going very slowly, or as opposed to the golf ball, which has a very small mass, it has to be going very fast. So the answer to the question, when can the golf ball and the bowling ball have the same momentum? It's when the golf ball has a large velocity. Now, there's actually also the sneaky answer to this question. The sneaky answer to this question is actually when both are at rest. Because if both are at rest, V is equal to 0, therefore the momentum would also be equal to 0. So if they were both at rest, or the golf ball had a super large velocity, because a large velocity and a small mass can be equal to a large mass and a small velocity. That is number one. Number two says, why is it safer for a driver to impact the airbag than it is for him to hit the windshield? Well, the thing about it is that if you're a car and you're going at 35 miles per hour, the driver in the car is also going at 35. And if the car comes to a stop, the driver is still moving forward. And so what happens is when the driver were to hit the windshield, right, you come to a very abrupt stop. So we're considering this as an idea, that the force times the time over which the force is applied is equal to the mass of the person times their change in velocity. Well, the person's mass and their change in velocity are going to be the same regardless. If we're going from 35 to 0, the change in velocity is 35, the person has the same mass. But if you hit the windshield, you're going to come to a very short stop, or a stop in a very short amount of time, so it's going to be a large force in a small time is going to give you a mass times the change in velocity. But if you hit the airbag, what it's going to do is it's going to increase the stopping time, therefore decrease the stopping force. So it increased the stopping time, which decreases the stopping force, which is what you want. This force is the force on you, and so that's why we have airbags in cars. It's also why we have seatbelts. Seatbelts aren't exactly stretchy, but they'll stop you on a much longer time than would the windshield. So there you go, that's number one and number two. Let's look at number three. Number three is a little bit out there. I don't love sports questions because not everybody's into sports, but this one I feel is kind of appropriate for the momentum. So number 3 says, baseball pitchers are tall. Why do you think they can impart such a large impulse to the ball? So this is number 3. So tall pitchers, and this is true for people in general. If you look at a short person, they have short arms. If you look at a tall person, they have much longer arms. So, longer arms, right? That doesn't mean they can apply more force to the ball, okay? They can apply the force for more time. Think about the throw. A short arm throw might look like this, okay? So there's the arm. Here's the ball. That throw might look like this. But a long arm throw is going to be like that. You can see that this is a small delta t, this is a large delta t. And so I think about the force times the time that the force is applied is going to be equal to the mass times the change in velocity. Same force, same mass. And so if you increase the time the force is applied, you can increase the change in velocity. More time gives you larger impulse, which results in a larger change in velocity. That one's kind of sneaky. Let's look at number 4. Here's a classic. A soccer ball with mass 0.4 kilograms shot toward the goalkeeper at a speed of 15 meters per second, hits head on and bounces back with a speed of 10 meters per second. So let's diagram this up. We'll do it over here. So here's the goalkeeper. Here comes the soccer ball. It's going to hit and then rebound back. The speed coming in is 15 meters per second. The speed going out is 10 meters per second. The mass is 0.4 kilograms. And the time of the contact is 0.02 seconds. So there's the diagram. Okay. All right, so there's our soccer ball. How much force did it supply to the head? Well, this is a classic force type problem here. So let's use the force times the time the force is applied is equal to the mass times the change in velocity. All right, that seems reasonable to me. So we're looking for the force. This is what we're looking for. I know the time, I know the mass. Can I get the change in velocity is the question. So force times the time is equal to the mass times, now change is always the final minus the initial. So I think I know all of these things. There's just one little trick here. It says it came in with a speed of 15 and left with a speed of 10. But this one is moving to the right, this one is moving to the left. So when I look at their velocities, this is a plus 15 velocity and this is a negative 10 velocity. So now when I go to plug in here, the time is 0.02, the mass is 0.4 kilograms. Now, the final velocity is negative 10 minus the initial velocity was 15. And then I'm going to calculate that. Negative 10 minus 15 is 25. You take that 25 and you multiply by 0.4, divide by your 0.02, and you have 500 newtons worth of force. So this problem is tricky because it really highlights the fact that this is the change in velocity, not the change in speed, but the change in velocity. And that velocity goes from 15 to negative 10, which is in essence a change of 25, or in this case negative 25 meters per second. That was really a sneaky one. All right, let's look at number 5. Now, the rest are all of the same type problem. Now, I know there was a little confusion in the beginning because in the original version of this, it referenced a picture, but there was no picture, which is super annoying. But let's diagram this up and see what it looks like. So this is number 5, probably 5 through 10, is it not? Let's start with number 5. So it says, some delinquent physics students put a large firecracker in a 6-kilogram bowling ball, initially at rest, light the fuse, and ran away. The ball breaks up into 2 pieces, a 2-kilogram and a 4-kilogram, which move away from one another. The 4-kilogram piece has a speed of 1 meter per second. All right, so here's the situation. Here's the before. Here's the after. In the before side, we just have a bowling ball. Now there's a firecracker in there and it's going to explode, but it's totally at rest, and then it explodes. And what it tells us here is it explodes into 2 pieces, a large piece and then a small piece that are moving away from one another. This one has a mass of 4 kilograms. This one has a mass of 2 kilograms. This one has a speed of 1 meter per second, this direction, and we're going to actually have to find out what the speed of that piece is. And there's a 6-kilogram bowling ball initially at rest. So here's our situation. So the first couple questions, so we're going to leave this diagram here. We can answer number 5 and then we'll go back. The first question says, how does the total momentum of the bowling ball system before compare with the momentum of the bowling ball system after? Well, this is called the law of conservation of momentum. Okay? I talked about this a lot. We talked about this as a group, is that the momentum, we use P for momentum, before an event and the momentum after the event always have to be equal. This word conservation here, that's a fancy science term, which means things don't change. So there's the conservation of momentum, there's the conservation of energy, energy before equals energy after, there's the conservation of mass, which you may have talked about in your chemistry class at one point, where on 2 sides of a reaction the total amount of mass has to stay the same. So this law, this conservation laws, we find them a lot, and this is the law of conservation of momentum. The total momentum before has to equal the total momentum after. So that's 5. Let's see what 6 asks. Six asks, what is the total value of momentum before the collision? Well, let's check. What's happening on the before side? We have just the bowling ball. If I want to calculate the total momentum, I'm going to take the total mass times the velocity. The total mass is 6 kilograms, but what's the velocity? 0. That means the total momentum before is equal to 0, and that's kilograms meters per second. So because nothing was moving, the total momentum has to be equal to 0. Now, what about 7 then? What is 7 going to say? 7 says, well, that's all fine and dandy, but what's the total momentum after? Well, if we know the momentum before was equal to 0, and we know the before has to be equal to the momentum after is also equal to 0 kilograms meters per second. Now, this is a little hard for you because you're like, but these guys are moving, and we're going to see what happens up here, because remember, this guy's moving to the right, so he has positive momentum. This guy is moving to the left, so he has negative momentum. When we add those up, it's going to end up being equal to 0. So the total can be and is 0, because that's the law. All right. Sorry, I'm checking my notes here. So it looks like number 8 somehow is a repeat of number 6. So that seems weird. I don't know how that happened. I'm going to blame Schoology on that one. So let's skip to 9. So 9 says, what is the speed of the 2 kilogram piece after? So let's use these momentum diagrams that we have been using since we started talking about momentum. To do this, I'm going to get our mass axis and our velocity axis. Here's the before side, here's the after side. Here's our system, and it's the whole bowling ball. Okay, it's the whole bowling ball. So that's in our system. And so when we go to diagram this up, here's what we'll do. We'll make this one purple. Well, that's the worst color for us. Make this one green. Make this one red. It's pink actually, that's adorable. All right, here we go. So what do we got here? So we have 6 kilograms. So I'm gonna make this 6. So 2, 4, 6. So the total is 6 kilograms. But when it breaks up into its 2 pieces, we know one of the pieces is 4 long. So it's 2, 4 long here. And the other piece is 2 long, about half that. So when I look over here, the thing that I notice that I think is important is that the total momentum is equal to 0. It's not moving, so there's no area. And if the total momentum here is 0, the total momentum here has to be 0. Well, how can that be? Well, then the thing it tells you is that this 4 kilogram piece is moving to the left with a speed of, moving to the left with a speed of 1 meter per second, so it's 4 kilograms. But its velocity is -1, so this area here is -4. But this one, it's 2 kilograms, and so how fast does it have to be moving? Well, you could use your brain and say, well, it's half the mass, therefore it does have twice the speed, and the answer is yes, it does. So this is a 2 kilogram piece, and it's moving at 2 meters per second, but it's moving to the right. That's +2, so this is +4, -4 and +4. And so the answer to what in essence is number 9. Number 9 says, what is the speed the speed of the 2 kilogram piece is equal to 2 meters per second. And now, what we're going to do is we're going to answer number 10. Number 10 says, how much energy was released to the pieces of the bowling ball during the explosion? Well, let's draw our energy bar charts. Okay? Let's draw our energy bar charts. So I have 3 energies we normally recognize: gravitational, kinetic, and elastic. Gravitational, kinetic, and elastic. Okay, I'm going to look at our system again. Our system is still just the bowling ball. So what I can notice here is that before, there's no gravitational, no kinetic, and no elastic, so the energy had to come from somewhere. But pause on that for a second. Let's calculate the energies over here and see what happens. So if I calculate the kinetic energy of the 4 kilogram, the kinetic energy is equal to 1/2 mv squared. The mass is 4, the speed is 1. So the kinetic energy is equal to 1 squared is 1, times 4 is 4, half of that is 2 joules. If I go to calculate the kinetic energy of the green piece here, kinetic energy, again, 1/2 mv squared. This one is 1/2 2 kilograms, and its speed is 2 squared. So its kinetic energy, 2 squared is 4, half of 2 is 1, so this is 4 joules. So when I go to put that on here, I'm going to say that there's 4 boxes of kinetic energy for the green one, and 2. And so the total amount of energy here, is 6 joules. But there was no gravitational, kinetic, or elastic, so where did it come from? Where did it come from? Obviously it came from the firecracker. How much? 6 joules worth. Anyway, that's the progress check. Looks like there was a problem with number 8. I will go back and I will edit this document later on. If you have any questions, let me know. I'm going to put this up for you guys to check over your work. Thanks so much.